Welcome to part 2 of lecture 16 on radiochemistry in reactors for chemistry 312. Part 2 will cover speciation of radionuclides in irradiated fuel, utilization of these resulting isotopes and how information about reactor chemistry and reactor behavior can be inferred, and a general discussion on fission product chemistry.
The fission process is necessary in reactors for the production of heat and the ultimate production in electricity. The fission process is also the source for the introduction of other elements into the fuel, whether they be fission products or actinides through capture. Now, in the fissioning process, and we reviewed this earlier, fission products will recoil about 10 microns in UO2 with a diameter range of about 6 nanometers. So imagine there's not a lot of straggling, very little distribution along the width of this recoil. So this happens to be of the size of a UO2 crystal. We already talked about Frankel pair production. There will be defects that will be formed, and there are some effects on this process on materials. One is radiation-induced creep, which is shown here. Creep, there's no volume change. There is a shape change, so imagine that something that would look like this can elongate. And this can happen with some, for instance, uranium metal, where if it was in cladding, it could elongate and breach the top of the cladding. Another effect is swelling. This is a volume increase. And this would be, so a cube here would just increase in size. This could be due to the fact that within the lattices you would have defects that would increase their size and swell the material. Another process that occurs in fission is relatively local high temperature. The temperature at the coolant cladding interface can be on the order of hundreds of degrees, where the local temperature of fission can be on the order of 3,000 degrees. We've already talked about some other processes associated with fission in fuel, delayed neutrons, and the fact that some fission products will undergo neutron capture. So this kind of changes their decay in the sense that if we were to look at a fission product, and I wanted to understand how its behavior, how much would be left at the end of irradiation, I would not only have to include its decay constant, so a saturation type effect, to understand how it would decay as it was being made, but also the fluence of the neutrons and its cross-section, because some of that fission product will capture neutrons and be transformed into other isotopes. So you have a decay effective, which is one based upon its regular decay constant, and then two, its cross-section with the neutrons in the material. So that will have an influence on the amount of a certain isotope, a fission product isotope, and if we're talking about amounts and material properties in chemistry, concentration effects can come into play about what is produced in the material. As we discussed earlier in the lectures on reactors, burnup is an important measurement, and it basically is used as a way to determine how much energy is extracted from the fuel. It could be terms in the percentage of the atoms that underwent fission, which is often done for fast reactors, or the actual energy release per mass of the initial fuel, which is done for light water reactors, and you get measurements in gigawatts days per metric ton or megawatt days per kilogram, and the units are shown here. A relationship between this is 1 MeV is equal to 4 times 10 to the minus 23rd megawatt hours. So there are some relationships with burnup as far as what one can look between these two burnup relationships. If I were to completely burn up my fuel in a light water reactor, the typical burnup would be 1,000 gigawatt days per metric ton heavy metal. Reactors don't come anywhere close to this value, and that's one of the reasons that reprocessing of this fuel is of interest, to try to achieve more energy utilization out of the spent fuel. Burnup can be determined either through calculations or through measurements. So what one can do is find residual concentration of the fissile nuclides in the fuel. after the irradiation. So if I know how much uranium-235 I have in the fuel initially, and I measure the amount of uranium-235 that remains, I can determine the burnup. For instance, with the uranium-235, however, you would also have to account for the neutron capture on the uranium-235, so you'd have to look at the amount of uranium-236 that's also present. Since if I just measured the initial and final amounts, the final amounts would be the difference between the initial and the amount of uranium that fissioned plus the amount of uranium-235 that underwent neutron capture. If you knew the neutron energy in the cross-sections, you can also use the cross-section ratios between fission and capture to calculate that amount. Or what you could do is find a fission product concentration in the fuel that is a suitable indicator for burnup. This would have to have a half-life that would be relatively easy to measure, not too short, not too long. And you need to know something about its nuclear data. I would need to know its cumulative fission yield, so I know how much of that isotope is produced per fission, and its neutron capture cross-section, based upon the equation on the previous page, so we would know how much of that isotope had been converted to a heavier isotope as it was sitting in the fuel. There are certain isotopes, cesium-137, neodymium-142, and europium-152 are often used as fission products to determine burnup. One can also look for neutron detection to determine burnup. You would need to minimize the influence of curium-244 because it is a spontaneous fission, so you need a route to measure the amount of curium-244 in the material. Burnup has an influence on the amount of radionuclides in fuel. We'll start by discussing the amount of actinides that can be in fuel as a function of burnup. And there are a few different types of fuel compositions one would need to consider. Natural uranium, where it's primarily uranium-235, some enriched uranium, shown here, or some MOX fuel, where there's an initial charge of plutonium, also available in the fuel. So this amount of plutonium in the fuel is going to influence the ultimate amount of actinides as a function of burnup. Particularly for americium, there's going to be a notable ingrowth of americium due to plutonium being present in the MOX fuel in the MOX fuel. What we see here are some differences in actinide concentration initially. If we look at the top table shown here, we have no plutonium. But if we look at the bottom table, which is MOX fuel, we have an initial level of plutonium. And one of the manifestations of that is the amount of americium. If we talk about grams per kilogram heavy metal as a function of burnup, without plutonium present, we have milligram quantities, whereas if plutonium is present, we have gram quantities. As a fuel undergoes fission, the amount of a given element will vary based upon the burnup of that material. And this is due to the ingrowth of isotopes and the decay of isotopes. So it's a very complicated system. And here's some data that's shown for the fission product element concentration in grams per kilogram of heavy metal in a radiated light water reactor uranium fuel that's been enriched to 4% uranium-235. And some of the important fission products that we see here include xenon. At a low burnup, it's 2 grams per kilogram of heavy metal, going all the way up to 10 grams. Xenon also has large neutron capture cross-sections, which is responsible for some poison behavior in fuel. After xenon, we would see molybdenum, also has relatively high amounts, again, a gram per kilogram heavy metal at a low burnup, up to 6 grams per kilogram at higher burnups. Zirconium, again, goes from 1.5 to 6. Cesium, 1.1 to about 5. Cerium, 1.3 to 5. And neodymium, from 1.4 to around 7. You see, the numbers are fairly consistent, but there are slight variations and this is again due to production of isotopes that have relatively short half-lives that are on the time, that could be on the time constant of the burnup of the fuel, and then also growth of certain isotopes due to decay from shorter-lived parents. Now, this is for, again, 4% 235. The chemical composition of the fuel has an influence. For instance, the ruthenium, rhodium, palladium have higher concentrations than plutonium-based fuel. So there's also a trend where the total activity of fuel seems to be is affected by radioactive saturation, where you get an equilibrium between growth and decay, and you get a maximum that tends to be reached. Now, the radionuclides that are produced are distributed within the fuel, and we'll discuss how they're distributed, and they're not always homogeneously distributed within fuel. As we show here, here's some activity in the fuel as a function of a radial distribution in two fuel types. One is a pressurized water reactor, and one is a boiling water reactor. And as we see with the PWR, there's a saturation, a constant level of activity in the middle of the fuel, and towards the edge of the fuel, the activity falls off. In this case, this behavior is due to neutron shielding effects from spacer grids, so there's a local decrease in fission rates right around the edge of the fuel. There's also some fuel density effects that can influence this behavior. So for instance, if fuel swells, there's a void, there won't be any fission in a certain area, and you can kind of see some small dips here. If there was a void here, it could be much larger. And also dishing at the end of the fuel, where you get the fuel has a concave shape, so you get a void in a certain area. The boiling water reactor shows an asymmetric fuel distribution, and this, for this particular example, this is due to control rod positions, so there's fewer neutrons in an area where the control rod is located due to the absorption of the neutrons by that control rod. So not only can we have an axial distribution of fission products within fuel, as we showed in the previous slide, but we also get some radial distribution. Now, this radial distribution of fission products and actinides is mainly governed by the neutron energy flux profile. So fundamentally, it has to deal with neutron reactions that are occurring radially within the fuel. One of the things that we do see is that there's a higher plutonium concentration on the outer zone of the fuel. As shown here, this lighter area, that's where the plutonium tends to reside. And here's a figure that if we see plutonium concentration in the fuel along its radial axis, we see as we get towards the edge of the fuel, so this is measured in microns, and here's the relative amount of plutonium, it goes up right at the edge. And this has to do with the fact that there's epithermal neutron capture on uranium-238 that preferentially occurs on the edge of the fuel. Epithermal are neutron energies that are between thermal and fast. So we get this high degree of capture, we get the preferential formation of uranium conversion into plutonium. This could also be a route if one wanted to treat fuel, if you could just treat fuel in a radial distribution. For instance, if I knew something about the rate of dissolution of fuel, I could preferentially remove the richer plutonium-containing segment of the fuel from the overall fuel. There's also a small influence on thermal migration of certain fission products, for instance, cesium, or other gaseous and volatile fission products. Noble elements are examples. There's also influence on the initial fuel composition, as we talked about earlier with some fission products, whether or not there's plutonium in a MOX fuel. The initial amount of oxygen can have an influence because oxides can be formed and prevent the formation of volatile species. And here's an example of some fission product distribution in fuel. The increase of this plutonium concentration on the rim leads to an increase in fission product density. If I have more plutonium on the rim, I can have more fissile material on the rim. Remember, the initial uranium fissile concentration in the fuel is about 4%. If I start just producing plutonium, I'm going to increase the amount of fissile isotopes on that rim. And and we actually see some effects with that. And that leads to some increase in fission product densities, and we see this here for cesium. We get a distribution, higher amount on the rim. We also see this for neodymium, higher amount on the rim, and zirconium, higher amount on the rim. Now, one of the differences we see between the neodymium, cesium, and zirconium, the neodymium and cesium, the neodymium and zirconium are relatively flat until you get to the rim, where the cesium has some character to this, where we see a higher concentration in the center. And again, this is due to some volatility behavior of cesium, which we don't see with the neodymium and the zirconium. We also see some behavior with xenon. Now, xenon, we actually see a decrease right on the edge here, and this is due to the fact that xenon is going to be extremely volatile in fuel, and what it'll do, it'll find locations where there's voids and congregate in those voids. There's also some variations in burnable poison. Gadolinium isotopes 157 and 155, used as burnable poisons, tend to be depleted in this outer zone. So we'll explore this thermal behavior and distribution in a little bit more detail. And the thermal behavior is mainly going to affect gaseous and volatile fission products. As we showed previously, the neodymium and zirconium, which would not be volatile, would not expect to be volatile, aren't influenced as much as these gaseous and volatile fission product species. One of the things that we can understand is pellet temperatures during the reaction operation will influence the behavior of these materials, and also the stoichiometry of the fuel, the role of oxygen in the fuel. If it's UO2 plus X, what X is exactly will have an influence on this volatile behavior. Some of the elements which are particularly, in addition to the noble gases, cesium and iodine have volatility behavior that can follow and used to understand some of the chemical composition of the fuel. Both of them have relatively high fission yields, and they have enhanced mobility within the fuel. In most cases, they can be treated similarly, which means that often one could imagine that the cesium and iodide could be even transporting as the same chemical form. An experiment was done where cesium iodide was added to UO2, and both elements have the same maximum location at 1,000 degrees. So this behavior, even at 1,000 degrees, was really just driven by the cesium iodide. The cesium and iodide were moving together. If one evaluated UO2 plus S, the iodine property changes. There was mobility to lower regions, and this is because you would have elemental I2 rather than I minus. So the oxygen would help oxidize the iodine, keeping it elemental. And this formation changed in the range of X up to 0.02. So just a relatively small amount of oxygen can help prevent the mobility of the iodine. Cesium itself did not change under these conditions. It remains monovalent, and its oxidation isn't going to be greatly influenced by just a small addition of oxygen from the UO2 plus X. What also was examined is that the release of cesium and iodine from fuel increases with temperature. So if we look over here to temperature and the relative amount of iodine and cesium released from fuel, we get a behavior that seems to go down and then spikes as temperature goes above 1,000 degrees. And this decrease is not observed for the cesium, but the continual increase above 1,000 degrees is shown for both of these elements. Not only do we see the overall amount of material being released, but the release rates increase with temperature. If you have a relatively high temperature, 2,100 K, there's a very large release rate in a very short period of time, 60 seconds. And we see that both elements can be released at significantly faster rates with higher burnup fuel. Here's an example of uranium burnup at 33,000 megawatt days per ton of uranium. And we see that the release of iodine and cesium, there's an initial increase and then reaches a the release reaches a constant rate as a function of time. There's somewhat different mechanisms for release, and these relate back to the behavior of the fuel, particularly any damage that was done due to higher burnup. And some of this behavior, also at higher burnup, is attributed to the fission products migrating towards the grain boundaries. We already discussed that the fission products themselves travel a distance on the equivalent of a fuel grain boundary, so they don't have to release themselves from the matrix of the fuel. They just migrate from the grain boundaries. And also, depending upon the fission products that's produced, the UO2 lattice may not be suitable for solubilizing larger atomic radii ions. So we could get different phase formation in the fuel. As the fuel fissions, fission products and actinides are going to be built up in the fuel itself. This could cause the formation of separate phases. Generally speaking, initially, when fission occurs, solid solutions are going to dominate because we're going to have a relatively low concentration of fission products. With increasing fission product development and actinide formation, secondary phases are possible. And these secondary phases begin to form when their solubility limits in UO2 are exceeded. One such material is perovskite, shown here as an ABO, where A can be mono or divalent, B are higher sites, higher oxide materials occupy the B sites. And what one could see for an example of a perovskite phase, shown here, this B site could be occupied by uranium, plutonium, zirconium, molybdenum, and the lanthanides. The A site could be occupied by the divalent barium strontium or the monovalent cesium. When solubility limits of these elements are reached, this material can be formed. For perovskite fuel, the mechanism seems to be driven by the initial formation of a perovskite composed of strontium and zirconium. When this phase is initially formed, eventually lanthanides are added at higher burnup when more of them are made. So evaluation of the perovskite phase can be useful in determining burnup information, since the composition of the perovskite will be directly reflecting the amount of fission products, hence the burnup of the fuel. Metallic phases can also form. These are called epsilon phases, and these materials are composed of the elements molybdenum, technetium, ruthenium, rhodium, and palladium. If one just a cursory examination of these elements on the periodic table, one of the properties is that they tend not to oxidize. So these metals above tend not to form oxides. If we have a limited amount of oxygen in the fuel, due to the only oxygen being available due to the UO2 or UO2 plus X, we can expect the formation of these metal phases. And what we see is that the grain size of these epsilon phases are generally around 1 micron, and their concentrations are nearly linear with burnup. So there's 5 grams per kilogram of uranium at a 10 megawatt days per kilogram uranium burnup, while it goes up to 15 grams per kilogram at 40 megawatt days per kilogram uranium. And as we see here, these phases will form in the boundaries between the fuel. And the formation of this metallic phase is promoted by higher linear heat. We see an example here of the heat formate, the Gibbs free energy of the oxidation as a function of heat formation. We can understand some properties of the fuel: 1, the relative heat, and 2, the UO2 amount. What we see here is this gap in the Gibbs free energy between some of the divalent, trivalent, tetravalent fission products and our fission products that compose the epsilon phase material. And what we see here is that depending upon the UO2 plus X, so UO 2.05, depending upon where the fuel was burnt, composition of material above this line would tend to be metallic, and below this line would tend to be oxide. So this gives you a good indication of what sort of composition of the epsilon phase one would expect based upon the initial UO2 plus X of the fuel. Now, molybdenum behavior is particularly strongly controlled by this. If we see the line for molybdenum, we see that it's much steeper than the other elements that are shown here. So the molybdenum behavior is controlled by the oxygen potential. Basically, the molybdenum tends to be very much in the metal if the metal to oxygen ratio is 2, and if it's above, if the oxygen to metal ratio is 2, and if it's above 2, if it's more oxygen, then more of the molybdenum is going to deposit in the UO2 lattice. So an overview of this behavior is shown here through some experiments that were done between 1400 and 1800 degrees centigrade. There was just trace irradiation of UO2 material, and the fission product behavior was evaluated. 4 categories were shown from this. You could have volatile fission products, metallic fission products, oxide fission products. There would be separate oxide phases, and solid solutions. Now again, this would tend to be at lower concentrations, but what's shown here is the volatile fission products tend to be the halides, the noble gases, rubidium, cesium. Metallic precipitates, what we discussed from this epsilon phases. Oxide precipitates, so separate oxide phases. These can also include the lanthanides, but those have to be at higher concentrations. And then the green are elements which are going to just form solid solutions with the UO2. And what we see is that some of the elements with the highest electronegativities have the highest mobilities, and these tend to form these volatile fission species. Some of the lower valent elements, such as cesium, barium, tend to have this behavior where they form separate species from the fuel due to their low valent cations, and their oxidation states don't match to the main fuel composition. And then obviously some neutral species will have low solubility, particularly something like xenon. These overall ions with higher charges tend to remain in the UO2. And neutral atoms or monovalent fission products tend to be mobile, and this is particularly evident at higher fuel temperatures. Within this lecture, we reviewed how uranium chemistry is linked with the chemistry in the fuel, particularly the UO2 plus X, how oxidation states of the fission products and the actinides in the fuel influence its behavior. The general trend is the lower the oxidation state, the less it's going to be soluble in the fuel, and what drives the speciation of actinides in the fuel, fundamentally how much of the actinides and fission products are in the fuel if they form separate phases. Something about volatility, those fission products which are volatile, how they behave in fuel, how they can migrate to certain areas of the fuel, how they behave if they get released in the fuel, and also some general trends in the fission product chemistry. 4 groups that are available and how fission products can fall into those groups on their behavior within the fuel, and how some fission products can cross the groups.
Some questions you should be able to answer from this lecture. What drives speciation of actinides and fission products in spent nuclear fuel? Well, the amount of fission. The more fission there is, the more the fission products can be involved in the chemistry with each other. And the type of fuel and the composition. So metallic fuel, there won't be any oxygen, whereas with oxide fuel, you can actually have UO2 plus X, so the amount of relative oxygen will slightly change the overall speciation of the actinides and the fission products. So what would be the difference between oxide and metallic fuel for fission product speciation? Well, as we already mentioned, the metallic fuel has no oxygen. So for the metallic fuel, you're only going to have the reaction of the fission products with uranium, so you may make some alloys, or you may make some binary phases, or the fission products can start interacting with each other, so you may have things like cesium iodide eventually form and react. And for this question, why do metallic phases form in oxide fuels? It has to do with the oxygen potential. So and the temperature at which the reactor is operating. So the fuel is operating at elevated temperatures, and depending upon the degree of oxygen available, so your UO2 plus X, you'll be able to get an idea of whether these noble metals, or these metals that form the epsilon phases, are going to preferentially form metals if they're above this UO2 plus X line, or if they're below it at the given temperature. And how is this behavior related to the technetium speciation in oxide fuel? Well, again, depending upon where your UO2 plus X lies and the temperature. So for instance, if it's UO2 0.05, when the temperature is below, let's say, about 800, technetium will be the oxide as opposed to the metal phase. So depending upon where this technetium potential for oxygen lives relative to the donating potential of the oxide fuel, you'll either get an oxygenated technetium, generally TCO2, or technetium metal. And often in fuel, you'll see mixtures of those species, particularly for something like molybdenum. This concludes Part 2 of Lecture 16 for Chemistry 312. This lecture was on the radiochemistry in nuclear reactors. When you've completed this lecture, please comment on the blog and respond to PDF Quiz 16.